Yes, so thank you. I got too excited with this. So yes, this becomes, okay, this is, okay, f of xy, if you will, or f of rho sine theta, rho phi and theta, if you will. But the official form is this crazy function. And what do we have? The rho, the phi, the theta, and this correction factor that, well, we're going to do it later using the Jacobian transformation at the end of the chapter. But in the meantime, we're going to derive it again geometrically, the same way we have derived all these versions of integrals in, from the basic integral to the one in polar. All right. Okay. So let's go back to the other page, the one, so we're going to define the volume element, all right? So that's a sphere, so over here we have a sphere. However, we're not going to look at a sphere in the same way that under the curve, our partition was to get a rectangle, get the area of that rectangle and add infinitely many of them. And then for the volume, for the volume, in 3 dimensions. For the volume in 3 dimensions, we got the volume of a rectangular prism, very analogous to the 2D idea. But in this case, we are going to take what we call, and that's a weird name, a spherical box. A box is rectangular, not spherical, and that's because, well, that's just a portion, a sample of the solid of a sphere, right? And well, so what we need to understand 3 things here. Number 1, in the same way that we had a delta x, delta y, and delta z, in this case, we're going to have 3 deltas here that will become later these 3 differentials, one for rho, one for phi, and one for theta. All right? So, number 1, the first delta in red, it's this one right here, and I think the perspective is great in this case. That's related to the thickness of the sphere, if you will. So that's going to be, let's call it delta out. Because in this case, we're going to go out of the sphere, right? We're going to go out of the origin. Whatever are rho units in this case, that's going to describe the radius of the sphere, all right? And well, this one is the simplest of the deltas that we're going to describe, because this thickness right here will be simply delta rho, all right? So that's the first delta. The second delta, okay, so we're going to have 2 more deltas. So let me go up to the picture here. So number 1, so we're going to have the set of spherical coordinates is governed by 2 angles. Number 1, the angle, if you will, the horizontal angle, all right, and a vertical angle. So in this case, let's look at the horizontal angle. All right, so that's going to be, let's call that delta around. All right, let's call it delta around. That's around the sphere. All right. And well, this picture doesn't look exactly circular. Okay, but this length in yellow is the same as this length in yellow. Does that look circular for you?
Like a pizza.
Yes, like a pizza. It's like the edge of a pizza. That's true. Well, the edge of a pizza, isn't that the arc length? All right, by definition, arc length equals r times theta. All right? In other words, okay, let's just use a letter for arc length. Arc length is S equals r theta. But in this case, to go from here, from this ray to this other ray right there, that involves a change in the angle, right? However, the question is, which angle is involved in between these 2 points? Is it theta or phi?
Theta.
Theta, because that's the angle around, not the angle, you know, the vertical angle, if you will. All right, so this means that we will define as r times delta theta in this case. However, well, our spherical coordinate system doesn't involve r, actually involves rho, all right? But we have a formula for r in terms of rho. We got it from the previous derivation. Isn't it this one I highlighted in green? Remember I highlighted because we were going to use it later? So this is when. So this is rho. Come on. This is rho sine phi delta theta. All right? So that's the delta around. All right. How about the delta? Let's define a third delta, which is, I mean, think of a planet. You were going around the equator, if you will, and in this case we're going maybe north or south. So that's going to be our vertical angle, if we will. All right. So let's call this delta. How did I call this one? Well, whatever that is. Delta, let's call it height. How about that? Height. Now we need to be very careful with this one. In this case, which angle is changing in this case? Phi. This one is, so this involves a delta phi, all right? This involves a delta phi, not a delta theta. The delta theta was for the delta around, not for the delta height, all right? Okay, the question is, which radius is involved right here? Rho, all right? Because this delta around, again, it's this little r, right? Is the radius r from the cylindrical or polar coordinates, but this one, the one that sweeps vertically, it's actually rho, and I think we have everything pretty much, all right? So delta v, if you will, that's basically, well, number one, in general, length, or rather volume, equals length times width times height. If we define this in terms of increments, that is in terms of deltas, that's delta v, which is delta L times delta W times delta H. So increment in the length, increment in the width, and increment in the height. In a similar way that we defined this one right here, delta x, delta y, delta z, but in this case, in general, with the geometric definitions, well, length, width, and height. All right, now in the context of spherical coordinates, our delta L, well, whatever they are, it doesn't matter. So ultimately, it will be the product of these three. This one, times this one, times this one. So that delta V will be then delta rho times r delta, I mean rho, not r, rho sine phi delta theta, and delta H in this case, not the enthalpy from chemistry, that's the height, and delta phi. All right, how about we simplify this a little bit? Well, rho times rho, that's rho squared, times sine, delta rho, delta phi, delta, actually I messed one up. This one was supposed to be at theta, delta theta. Does that look familiar? Well, that's the finite element. That's the partition. You know, take one element, analyze it, like over there. Take one rectangle, find the area. Now add infinitely many of this. This is the same dv rho squared sine phi d rho d phi d theta. So this is where all this madness right here is coming from. All this dv, that's the volume, based on the volume of weird name, spherical box. The reason I go over all these details, number one, because some of you may have to take some upper division courses in mathematics and engineering, and actually those of you who are taking physics too, I think you're going to look at spherical coordinates, and when it comes to defining what's this, electrical fields, magnetic fields, so you'll have to solve some problems involving all this system, and it's important to know how it works, where is it coming from. That may save you a lot of pain when solving certain problems, all right? And well, Genesis, your math major, this is also good for you. Any other math majors by any chance? Your math major, so yeah, you're gonna need this, all right? So, and plus I think it's pretty cool derivations, isn't it? Actually, it gives you an idea where it's coming from. It gives you a sense of, we're not just crunching numbers and symbols. Well, yes, we are in a way, but I think it gives us a better idea of how things work, you know? All right, so how about we set up some integrals in spherical coordinates, all right? So convert to spherical coordinates, then evaluate integrals from 0 to 3, integral 0 to the square root of 9 minus x squared, so integral from 0 to the square root of 9 minus x squared minus y squared of, and that integrand square root of x squared plus y squared plus z squared. Well, number one, try to evaluate the integral as is. We wouldn't be able to do it, because when we set up the integral with respect to z substitution, what's the derivative of z squared? We would need a factor of z outside, right, to stand the du part, which we don't have, so that's why spherical coordinates, all right? Okay, so let's start by analyzing all these pieces of information. Recall that all these limits of integration gives us an idea of what's going on in the xy plane, in the solid region, and on the x-axis, which is pretty much the last, or rather the outermost integral. Oops. All right. So, how about we start by changing the integrand into spherical coordinates? What is that equal to?
R squared. Something.
This is simply rho, right? Because, okay, so x squared plus y squared plus z squared, you can think of the distance formula in 3 dimensions, or the radius of the sphere, right? But the square root of that's just rho, all right? Or the Pythagorean theorem in 3 dimensions, if you will. All right, so we got something, all right. So the innermost integral is telling us that z is varying between 0 and the square root of 9 minus x squared minus y squared. All right. Now let's look at the rightmost side of the compound inequality. This means that z is less than or equal. Okay, let's take the equal part. 9 minus x squared minus y squared, and we'll square both sides. That's c squared equals 9 minus x squared minus y squared, and having all variables on the left hand side, that's x squared plus y squared plus z squared equals to 9. All right. This means Isn't that a rho squared, which equals to 9? So rho equals to 3. All right? So now that we change this equation in terms of cylindrical coordinates, from here we get that z is, or rather, yes, z, no, not z, never mind. Rho is varying between 0 and 3. In other words, check the upper limit of integration, or just check this equation right here. Isn't this equation that of a sphere center at the origin with a radius equals to 3? Alright, so the outermost bound will be all those points that are 3 units away from the origin. And in this case, that tells us the rho varies between the origin 0 and 3. Alright? Okay, what's next? What else can we get from here? Alright. One thing to observe. Check this out. Careful with this. The limits of the second inner integral. So when you see y, in this case, when you see y, okay, when we see this integral, this is telling us that y is varying between 0 and the square root of 4 or 9 minus x squared, isn't it? Okay, so y varies between 0 and the square root of 9 minus x squared. Well, what is this telling us in picture? But it's only the upper part of the circle, isn't it? It's not telling us between negative radical and positive radical. That will tell us the entire circle. In this case, the positive radical implies that it's only the upper part of the circle, the upper semicircle. So let's write that down. So that's the top half of the circle. And well, this thing about circle shouldn't be a surprise because the circle is the projection of the sphere in the xy plane. All right, just to keep checking for consistency with what we're doing. The top of this, okay, the top part of the circle. That means from here we can get that the upper semicircle of radius 3, 1, 2, 3, 1, 2, 3. All right. And in this case, well, what about the outermost limits of integration? Oops. The outermost limits of integration, the ones with respect z, is telling us that the radius r is from 0 to 3, which is consistent with the radius of the sphere as well, right? So this means, in this case, then, that x is varying between 0 and 3. All right. So what do we got? What do we have already in spherical coordinates? So we have rho. All right. We have that rho is varying between 0 and 3. Let's start writing the triple integral. So that's going to be, okay, so this madness right here is just rho. Okay, and this dz, dy, dx becomes r squared sine phi d rho d phi d theta, all of that. All right, let me write it in a different color just so we can distinguish it from the integrand. All right, so that's times rho squared sine phi d rho d phi d theta. All right, so let's start writing the limits of integration. So we already have limits of integration for rho, which in this case is 0 to 3. All right. Now, the innermost limits of integration in a very similar way that the second integral. So the second integral was telling us that we were looking only at the upper semicircle. The innermost limits of integration are telling us that we're looking at only the upper hemisphere. Do you guys agree with this? Because otherwise, this would have said instead negative root of 9 minus x squared plus y squared. Alright, that would have said the lower hemisphere to the upper hemisphere. Alright? So, this being said, all that being said, let's draw a picture in 3D. We want only that doesn't look like a sphere anyway. I give up on this one. So the upper hemisphere. All right. Okay. Can I maybe? Okay. And that's to determine the angle phi. So we have the sphere right here. For the angle phi, which is actually the angle that varies from the positive z-axis to the negative z-axis, how far does it go? Only up to pi over 2, right? It goes as far as pi over 2. Alright? So it goes from 0 to pi over 2. So
that's only like the upper.
Yeah, exactly. 0 to pi over 2, because that's only the upper hemisphere. If it were the entire sphere, it would have been from 0 to pi. All right. And well, what about theta? Theta is the angle in the plane, in the xy plane. But what do we have in this case? How far does it go? From 0 to pi, right? Because it doesn't go around the whole circle. From 0 to pi. All right? Okay, what time is it now? We have enough time. Yes. Okay. So let's evaluate this integral, which actually is not as bad as it looks. I think the hardest part is the setup. Right? The hardest part is the setup, and even if you try to evaluate the integral as is, it's actually impossible with the methods that we know to integrate. All right. So this is the triple 0, 0, 0 to pi over 2 and 3. That's rho cubed sine phi d rho d phi d theta. So we're going to integrate with respect to rho. So the integral of rho cubed with respect to rho, that's going to be the integral from 0 to pi, the integral from 0 to pi over 2, that's rho to the 4th over 4. Evaluate from 0 to 3. Then don't forget, let me actually write the sine phi from 0 to 3. D phi, d theta. And again, recall that we are going to do the fundamental theorem of calculus only in the variable rho. So we have in our integrand, so far we have a rho and a phi. So just careful where you're plugging these values. So that means the double integral from 0 to pi and from 0 to pi over 2, and that's going to be 1/4 3 to the 4 power minus 0 to the 4 power sine phi d phi d theta. And then, well, what do we have? 3 to the 4 power, isn't that 81? Minus 0, that's 81. Divided by 4, that's just 81 over 4. That's the double integral from 0 to pi. And from 0 to pi over 2, so that's 81 over 4 sine of phi d theta. So we're done with the first integration. Let's go about the second integration. That's the integration with respect phi. So what's the integral of sine? Careful. Negative cosine. So that's going to be the not the double integral, just a simple, the single integral from 0 to pi. And that's negative 81 over 4 sine. And that goes evaluated from 0 to pi over 2 d theta. Upper limit minus lower limit, well, that's the integral from 0 to pi. That's what I meant, but not what I wrote, right? Cosine, negative cosine. So that's a negative 81 over 4 cosine of pi over 2 minus cosine 0 d theta. And well, cosine of pi over 2, isn't that a 0? And cosine 0 is 1. Well, so this negative 81 gets multiplied with negative 1 and becomes positive. So that's the integral from 0 to pi, 81 over 4 d theta. That's, okay, let me take the constant out of the integral, 0 to pi. And that's d theta. And just integrate 81 over 4 theta from 0 to pi. And 81 over 4 well, actually, oh no, never mind. So that's 81 over 4. Oh yes, 81 over 4 times pi minus 0. And that's 81 pi over 4. All right. Right? Well, ultimately, all this madness, what are we really doing? What are we calculating? Well, let's observe the integral and see what it looks like. So, recall that the triple integral dv, when the integral is only an invisible one, that represents volume, right? However, when the triple integral has some f of x, y, z, or in cylindrical or spherical, I'm not going to write all that mess, dv. So the integral represents the volume, and that function represents the density function. And when we calculate this triple integral, what we're really calculating here is the mass of this sphere in the first octant. All right? In the first octant. That's what we're calculating. Well, actually, no, the first and the second octant, because it goes from the around angle goes from 0 to pi, so we get a quarter of the sphere, if you will. All right, the mass of a quarter of a sphere with a density that is variable, and that density varies at different points under this function right here. All right. What's next?